In this video, we are going to learn how to match features between two images. Specifically, we will talk about how to detect and extract features, how to match features, and how to visualize these features. This training will be useful for all AUVSI teams as it talks about the fundamental image processing and computer vision concept of detecting and matching features. We would also like to thank the Cedarville University RoboBoard team for providing us with image and video files for us to use in this training. Let's start with a simple example. Say you have two frames from a video like this. Here, the green buoys in each of these images is the same buoy taken from the same camera at different angles. We would like to match the green buoys in these two images. The application could be, for example, to track the buoy or to perform image reorientation. This can be done using feature matching. What are features? Features are interesting parts about a particular image that will aid us in uniquely identifying the image to perform the necessary computer vision task. Some examples of features are shown here. Corner points, edge artifacts, and uniform intensity regions are all interesting to us to do various tasks. Consequently, the feature of interest to us depends on our application. For our two images here, we would like to match the features between these two images to match the green buoys here. This would in turn require us to automatically detect, extract, and match the corresponding features between the two frames. We will now explore the various ways to do this in MATLAB. A common first step to do feature matching is to detect corners. Corner detection can be done in Computer Vision System Toolbox using several different algorithms, namely BRISK, FAST, Harris, or minimum eigenvalue algorithms. All these functions take in a grayscale image as input and based on the algorithm have different tunable parameters which affect the output of the detection. Let's switch to MATLAB and see how we can do this. Let's open up a starter script here, detect features _ start. This script has several comments that will help us build our algorithm here. Let's begin by loading a couple of sample frames that contains the objects of interest to us and then visualize them using subplots and IMShow like we did in the blob analysis video. So here I can say load sample frames.mat, which is the file that has our sample frames. And then to visualize this frame, we can say subplot 1, 2, 1, and then use the IMShow command and provide the name of the video frame. In this case, vidframe1. Let's go ahead and provide a title to this image as well. So in this case, I'm going to call it original frame. Since the feature detection algorithm works on grayscale images, we need to convert this RGB image of the original frame into an intensity image or a grayscale image. To do this, we can use the RGB to gray function. Recall that we used the RGB to HSV function in our blob analysis video. So here I can say RGB to gray and then provide the name of the video frame here. So in this case, it is vidframe1. The output of this is also an image, so I can provide a name here, in this case, gray frame. Let's go ahead and visualize this as well. So I'm going to copy the visualization code here using Ctrl+C and then paste it here. And then here I can say subplot 1, 2, 2, and then IMShow of gray frame instead of our video frame 1, and then change the title also. So in this case, it is grayscale frame. Now that we have a grayscale version of the video frame, we can use a feature detection function on this image. We will begin with a detect min eigenfeatures function that uses the minimum eigenvalue algorithm to detect the corners. This algorithm is good for image registration with little or no scale change. So here I can say features equals detect min eigenfeatures. Notice that I use the tab key on my keyboard to autocomplete this function again. The input to this function is the grayscale image first, so in this case that is called gray frame. Let's go ahead and save the script here as detect features underscore min, which stands for minimum eigenvalue here. And then let's go ahead and run the script here. So here is our original frame, and here is our grayscale frame. Let's go back to the MATLAB command prompt here. Features here is the output of our detect min eigenfeatures function. Most feature detection functions return a corner points variable. Let's type in features here. A corner points variable is characterized by the location, metric, and count properties. Location stores the x, y point coordinates of the detected corners. Metric tells us what is the strength of a particular corner. And count tells us the number of detected corners. We can use the plot function with these corner point variables to show the locations of the corners on the original image. To do this, let's go back to our script here. So here, I'm going to go ahead and copy the visualization code here, and then go ahead and paste it here. And let's plot this in a new figure here. So here we have IMShow of video frame 1. And then we can say hold on, and then use plot on our features variable here to plot our features on the original video frame. So here I'm going to say all features. Let's clear our workspace and close all our figures here, and then run the script again. So in this image, we can see all the features that have been detected by the detect min eigenfeatures function. Corners look for sharp edges, hence we see that there are several features detected around the tree line here because of the high contrast. Let's zoom in here. We can see that the algorithm has picked some corners around the green buoy here as well. Let's go back to the original view here. Now, among all these corners, we can select the strongest corners based on the metric property. To do this, we can use the select strongest function. So let's go back to our script here. So here we can say specific features equals select strongest of the output of our detect min eigenfeatures function. So in this case, that is features, and then provide the number of strongest points that we need. So in this case, I'm going to specify 100. Let's go ahead and copy the visualization code here, and then paste it here. And then here I can say subplot 1, 2, 2. And then on our original frame, we are going to plot specific features. And then here I can say strongest 100 features. Let's go ahead and close all our figures, clear our workspace, and then run the script here. Now on the right image here, note how the corners around the green buoys have disappeared. This means those corners were not among the 100 strongest. However, the tree line features are still detected nicely because of the high contrast. Since our objective is to detect the green buoy reliably, let's go ahead and try another algorithm. Let's try the BRISK algorithm next to detect features in this image. This algorithm particularly handles scale and rotation changes well. Let's go back to the script here. Let's go ahead and copy all the commands in the script. So I'm going to press Ctrl A on my keyboard and then Ctrl C to copy all these commands. Let's create a new script by clicking on this plus button here. Let's go ahead and paste all these commands by pressing Ctrl V on the new script here. Since we are going to be using the BRISK algorithm, let's go ahead and save this script as detect features underscore BRISK here. Let's go ahead and save this. Let's go back to the top here. We will leave the code here for loading the frames and converting the frame to grayscale. To detect the features using the BRISK algorithm, we will use the detect BRISK features function. So let's scroll down here. So instead of detect min eigenfeatures, we can replace this with the detect BRISK features function. Notice that this function also accepts the grayscale image as input. And let's go ahead and run this section here. Let's take a look at this output here. Let's go ahead and zoom in around the green buoy here. We can see that there are not many features detected around the green buoy. Let's go back to the MATLAB command prompt here. Let's type in features. Notice that the detect BRISK features function now returns a BRISK points variable instead of a corner points variable. The only difference between the BRISK point variable and the corner points variable is that the BRISK points variable has extra properties called orientation and scale of the detected feature. BRISK is a multi-scale detection algorithm that can handle changes in scale and rotation as discussed before. These scales are called octaves, and you can set the number of octaves by setting the num octaves property. Let's go back to the script and see how we can do that. So let's copy the command here, detect BRISK features of the gray frame, and then paste it here. And while calling this function, let's go ahead and set the num octaves property. The default value for this is 4. Decreasing the value for this will detect smaller blobs, hence makes the algorithm more selective. So let's go ahead and set this to 1 here, which is less than the default value. Now let's go ahead and change the title for these images here. So I'm going to say this is num octave 4, and this is num octave 1. Let's go ahead and close our figures and clear our workspace and run the script here. Let's take a look at this output here. Notice that decreasing the number of octaves here is starting to detect smaller blobs. If we zoom around the green buoy on the right-hand side image here, we are still unable to detect the green buoy reliably in this method. Let's go back to the original view here. Not all images will have defined corner, and you may want to use uniform intensity regions for feature detection and matching. This could be achieved by using the detect MSER features function. MSER stands for maximally stable extremal regions. To see how to do this, let's go back to the script here. Copy all these commands using Ctrl A and then Ctrl C. Open up a new script here and then press Ctrl V to paste all these commands here. Let's go ahead and save the script as detect features underscore MSER. Let's go back to the top here. We will leave the code here for loading frames and converting it to grayscale. To detect uniform intensity regions, we will use the detect MSER features function. So here I can say, instead of detect BRISK features, detect MSER features. Again, this function also takes in a grayscale image as input. The output of the MSER features function can also be plotted using the plot function here. Let's go ahead and rename this title here to all features. And then go ahead and run this section here and take a look at this output. Let's go ahead and zoom in around the green buoy here. We can see that there are many features detected around the green buoy. So this algorithm seems to perform better than the two previous algorithms that we used. Let's go back to the MATLAB command prompt here. Notice also that features now is a MSER regions variable, which has a different set of properties such as count, location, axis, orientation, and pixel list. As we discussed before, the MSER algorithm is used to detect uniform intensity regions. It does this by incrementally stepping through the intensity range of the input image to detect the stable regions. By controlling the step size of this intensity, we can be more selective about the regions returned. We can do this using the threshold delta property of the algorithm. Let's go back to the script to see how we can do this. So here, I'm going to go ahead and copy the detect MSER features command here, and then paste it here. And let's go ahead and set the threshold delta property. The default value for this property is 2. By increasing the value of this property, we can be more selective about the regions returned. So in this case, I'm going to set it to 4. Now let's go ahead and change the title here. So here we are going to say threshold delta is 4. We can copy this and then paste this here, and then note that this is threshold delta 2. Let's go ahead and close our figures, clear our workspace, and then run the script here. Let's go ahead and take a look at this output. Let's go ahead and zoom in around the green buoy when we set the threshold delta to 4. So here, even the selective algorithm is able to detect the green buoy reliably well. Let's go back to the original view here. We also see the number of features detected around the tree line to be reduced. And this is because the MSER algorithm uses an intensity-based approach as opposed to the other algorithm, which are more sensitive to contrast. Let's go back to the presentation for a recap. We saw the properties of the corner points variable, namely count, location, and metric. We also saw how to select the strongest n detected corners based on the metric. Note also on the checkerboard image here that the higher contrast corners are deemed to be the stronger corners. We then discussed the BRISK algorithm, which handles scale change and rotation. Particularly, we saw how changing the number of octaves affected the algorithm. We can increase this value to detect larger blobs. Similarly, there are other properties such as min contrast and min quality which can be tuned to affect the results of the BRISK algorithm. At this point, we were still unable to detect the green buoy with certainty. We discussed how not all images will have defined corners, and we may want to use uniform intensity regions for feature detection and matching. We did this using the detect MSER features function. We were able to reliably detect the green buoys after this. Recall at this point that our final objective is to match the green buoys in two different images and not just detect a green buoy in a particular image. The next step to do this is feature extraction. Features detected using the corner detection algorithms do not necessarily correspond to physical structures such as the corners of a table. The key to feature detection is to find features that remain locally invariant so that you can detect them even in presence of rotation or scale change. This can be achieved by feature extraction, which only extracts features which are repeatably detectable, meaning features are robust to changes in viewing conditions and noise. Distinctive, meaning the neighborhood around the feature center varies enough to allow for reliable comparison between features. And localizable, meaning the feature has a unique location assigned to it. For the already detected corners of an image, you can extract feature descriptors using the extract features function. Once you have extracted the features, you can match the features between two input feature sets using the match features function. This function returns the indices of the matching features. You can then visualize these matched features by feeding them to the show matched features function. Let's go back to MATLAB to see how we can do this. Let's open up a starter script, in this case match frames underscore start. We begin by loading a couple of frames that we can use to match features, so let's go ahead and run this section here. So here we see the original frame in color and the grayscale images that we are going to be using to extract and match features. Let's go back to the script here. The first step for feature matching is detection, which is what we are doing here for both the frames. We are going to be using the results of the MSER algorithm for the rest of the example, although the workflow to match features remains the same no matter which feature detection algorithm is being used. Let's go ahead and run this section here. Then we can use a combination of imshow, hold on command, and plot to visualize the detected features. Let's go ahead and run this section here. So here we see the two frames and their detected features here. The next step is to extract feature descriptors for each of these two frames using the extract features function. To do this, let's go back to our script here. Let's use the extract features function. The first input is the image for which we are doing feature detection. So in this case, that is gray frame 1, followed by the output of the feature detection for this frame. So in this case, it's going to be MSER regions 1. The output of this function is the list of feature descriptors and their location points. So here we can say features 1, points 1. This is the feature extraction for the first frame. We need to do the same thing for the second frame. So let's go ahead and copy this command and then paste it here. And then we are going to rename these variables as features2 and points2 and provide gray frame 2 as the input and MSER regions 2 as the second input. The output location points here can be visualized using the plot command. To do this, let's go above here and then copy the visualization commands here and then paste it here. Notice that we are visualizing MSER regions 1 and MSER regions 2 here. We will replace them using points 1 and points 2. Let's go ahead and change the title here. We're going to call this extracted features instead of detected features. Let's go back to the extract features section here. Go ahead and run this to generate our points variables. And then run the visualization code here to take a look at the extracted features here. Now that we have a set of feature descriptors for each of these two frames, the next step is to match these features. To do this, we can use the match features function. Let's go back to our script here. So we can use the match features function. and provide the two features that we have extracted as inputs. So we can say features 1 and features 2. The output of the match feature function is the indices of the matching features in the two input feature sets. So let's assign the output of the match features function to the variable index pairs. This index pairs variable can then be used to drill down our matching points using indexing. So here we can say matched points 1 equals, use our points1 variable, which is all the points that have been extracted as features for our image, and then find only the points that were returned by the match features function. So here I can say index pairs of colon comma 1, which belongs to the first frame here. Similarly, copy this command here and then paste this here. So the second set of matched points here will be the points2 variable, but only the index returned by the match features function. The matched points here can then be visualized using the show matched features function. So let's go ahead and do that here. Show matched features of, it takes in the two input images for which we are showing the matched features. So in this case, that will be with frame 1 and with frame 2, followed by their respective matched points. So in this case, it will be matched points 1 and matched points 2, followed by a display method. This property determines how we are going to visualize the matched features and can be set to a variety of things. Please refer to the documentation for more information of what types of display methods are available. For this example, we are going to use montage that places the images side by side and matches the features across the points using lines and markers. So let's go ahead and set this to montage here. And let's make sure we show the matched features in a new figure. Let's close our figures, clear our workspace, and then run the script here. Let's go ahead and take a look at this output of matched features here. So here we can see the two green buoys that are matched, apart from the other matched features that we can see in the background. There are some erroneous matches, for example, the reflection here. These can be eliminated by experimenting with various parameters of the feature detection algorithm. At several points during this video, we discussed various feature detection algorithms and when to use them. Please refer to the documentation to get more information on which detection method to use in which scenarios to help you choose the right approach for your application. Let's go back to the presentation and do a small recap. In summary, we detected and extracted features from images using various algorithms, for example, BRISK and MSER, and matched them between the two frames. We also saw some simple techniques to visualize these features using the plot and show matched feature functions. This concludes this video.